Good morning everyone. Today I will be talking about characterization of materials. So, until now you guys might have already studied about what are biomaterials and different types and what are its application and all. So, now you have to learn why we need to characterize the materials. So, materials, when we are characterizing, we will make it to understand the properties, so that it can be whether a material is accepted as a implant or a medical devices and all. So, the biocompatibility of the material is primarily dependent on its property. So, to find out its properties, we have to characterize the materials. So, for developing a new materials also, you have to understand the new properties, so that it mimics the natural existing organs and other applications and all. So, to identify those properties also, you need to characterize the materials. The material characterization is primarily divided into two categories. One is based on the engineering properties such as surface properties, mechanical properties, chemical and physical properties, and other is totally dependent on biological relationship with the material, which is in vitro biocompatibility, in vivo biocompatibility. So, surface properties. So, surface property is the property primarily dependent on the material and the host cell interfaces. So, when a material is implanted into the body, the first point of contact is the material surface and the host cells. So, the surface should be biocompatible, so that it will not be rejected by the host mechanism. Mechanical properties, well, you are considering implants such as hip prosthesis and other heavy load bearing applications and all, you need to have a good mechanical property, which will be understood by characterizing the bulk properties of the material. That can be done using the mechanical characterization. Physical and chemical properties. So, physical and chemical properties involves understanding the material composition and what are its thermal properties and what are its, if you are using a scaffold for tissue engineering applications and all, you have to understand the porosity and the permeability and how much the water intake it can actually have. So, those properties and all come under chemical and physical properties. In vitro biocompatibility. So, before going for the clinical application, we have to previously test the material with in vitro and in vivo testings. So, in vitro biocompatibility involves whether the material is suitable for the cell adhesion, whether there is a immunogenic response from the cells we are in vitro studies we are doing, whether there is a protein adsorption, whether there is a blood coagulation occurs on the material surfaces and all. In vivo biocompatibility involves testing the material in animal models like rats, pig and dog models and all, to check whether the material has a same function when you are introducing into a human body. So, after all these properties has been done for both at the biomaterial level and the biomedical devices level. It cannot be only for material. If a material, I am preparing a material, and if it is a biocompatible, we cannot say that will be exactly replicated in the devices also, because device will have a different structure and different totally function varies. So, you have to check in the biomaterial level at first, then you have to go for the biomedical applications also. And all these properties cannot be applied for all the materials. So, it depends on what type of material. Some are nanoparticles, some are films, and some are scaffolds, some are huge bulk materials and also each of these materials will have to be characterized based on the material properties, what type of characterization you have to look and what type of application you are going to look into. So, coming into characterization techniques, these are the predominantly 5 different types. Surface characterization, what are the techniques you can, there are lot of techniques available for the lot of properties, but these are the widely used techniques used in the biomaterial field. So, surface characterization techniques such as wettability or contact angle measurement, this is a technique where you will find a material surface is hydrophobic or hydrophilic. Hydrophobic is water repelling and hydrophilic is water attracting. X-ray photoelectron spectroscopy, which will calculate the elemental composition of the material. What are the elements present on your material surface and what are the chemical bonds present on the material surface, that can be found out using XPS analysis. Secondly, ion mass spectroscopy, it is also a surface technique where you can find out the surface particular atomic composition of the material, whether the how much electron available on the material surfaces and all, those can be calculated by secondary ion mass spectroscopy. So, microscopy techniques also comes under the surface characterization, but there are a lot of microscopic techniques available. So, one of the mainly used technique is scanning electron microscopy, that is used to observe the morphology of the material surfaces and all. Then transmission electron microscopy, which is used to see the inside the material surfaces and all. So, I will explain both of those techniques later. Atomic force microscopy, it will check the surface roughness of the materials. So, you can check how much of the material surface is smooth or whether it is rough. Those parameters will greatly affect the cell attachment and other properties. Then optical microscope will have a variety of microscopic techniques such as phase contrast, fluorescent microscope, confocal microscope, all of those comes under optical microscopy. Physicochemical characterization involves FTIR, which will characterize the functional groups present on the materials. NMR spectroscopy, you can find out what are the bondings available on the, what are the bondings and what are the elements present on the materials. X-ray diffraction will tell whether the polymer is amorphous, crystalline or semi-crystalline, these things. DSC and TGA analysis is a thermal property characterization techniques where you will find out the melting point, degradation, glass transition temperature, those kind of properties can be found out using DSC and TGA analysis. Mechanical characterization is hugely important for the bulk load bearing applications. So, those experiments involve tension and compression, how much of a load it can withstand and how much of compression it can go, fatigue, how long it can be available without any breaking or those things, creep and viscous flow, how the polymer actually works inside the host system. Then biological characterization, protein adsorption study, because the first when you implant a material into a host system, the first interaction between the host system and the material is the protein adsorption. So, if there is a protein adsorption occurring on your material surface, then that will lead to cell attachment and blood cells attachment also. So, based on the application that can vary. So, if you want your material to not to have any attachment of cells, it should not have any protein adsorption on the material surface, because when you are going for the blood contacting devices and all, there you do not need blood cells to attach onto the material surface, because it will lead to blood clot formation inside the devices, which will lead to failure of the device. So, for those applications we have to check for the protein adsorption studies, and if you are going for the tissue engineering application like wound healing and these things, so you need to have cells attached onto the surfaces and all. So, for that application you have to have a protein adsorption on the material surfaces and all. So, these are the basic techniques. Other than this, there are still lot of techniques are available, which is specific for each of the application we have to look into. So, coming into surface characterization techniques, as I told you earlier, contact angle analysis, XPS, Auger electron spectroscopy, which involves the Auger electrons, then secondary ion mass spectroscopy, which is known as SIMS, then FTIR, STM is scanning tunneling microscopy, then scanning electron microscopy. So, each of technique has a different resolution of how much properties you can identify using those techniques and the cost they have given. So, all these atomic related composition finding techniques and all will be very highly costly. So, the basic techniques like contact angle analysis, FTIR and all, it is slightly lesser. So, while developing a new materials and all, you can first optimize those materials using the basic techniques, then you can go for the higher end techniques to confirm whether that material has been properly based on your application and all. Okay. So, each of the application I have told you already. So, let us go into contact angle measurement. So, contact angle measurement is to determine the wettability of the surface and to estimate the surface energy. So, when a material is introduced, the first the liquid solution from the host mechanism will spread on the material surface. So, that primarily affects how the proteins are absorbing, how the cells are absorbing on the material surface and all. So, to find out that wettability property, whether the material is hydrophobic or hydrophilic, we have to use the contact angle measurement. So, the angle between the solid liquid interface and the liquid interface is the contact angle. So, this relation has been given by Young's equation, which is interfacial tension between the solid liquid interface cos theta equal to interfacial energy at solid vapor minus interfacial energy solid liquid interfaces. So, based on this contact angle, we can modify the surfaces also. So, already a existing material is available and you want to improve the properties of the existing materials and all. So, you coat a material surface using a different polymer or some other treatment available, modification techniques available and all. So, if you do that, the contact angle can be varied. So, by varying the surface property, you can actually have the better cell attachment, better protein absorption and all those things available. So, if a material is above 90 degree, it is hydrophobic. If it is below 90 degree, it is hydrophilic. Okay. If a material is above 150 and all, it is super hydrophobic, which is known as lotus effect, where you see a water droplet on a lotus leaf, where the water will retain its bead structure on throughout the surface. That is called lotus effect due to its micro structure on the lotus leaf available. So, for measuring the contact angle, we use an instrument called goniometer, contact angle goniometer. So, there are different types of measuring contact angle available. One is a sessile drop method, which is the widely used technique. So, the picture A, where you can see there is a material surface and you put a drop on the material surface and you measure the angle between the solid liquid interface and the liquid interfaces. So, you draw a tangent at the point of contact and measure the angle between the angle on that area, interface area. So, that will give you the contact angle, that will show whether the material is hydrophobic or hydrophilic. Then captive air bubble method, which is similar to the sessile drop method, but instead of using a liquid, we use a air bubble to measure the angle, contact angle. So, you have a material surface and it is immersed in a liquid solution and you introduce a drop on the bottom of the surface. So, it will form a bead like structure, which will give you the angle between the liquid interface and the solid surface, which is the contact angle. So, why we can use, where we can use for the captive air bubble measurement is when your material is intaking water and all. So, if you are just doing it in an air atmosphere, so the material will hydrate and it will absorb all the water into the material itself. So, if you are using a air bubble method, so it will show the angle because it will be already hydrated with the liquid present on the surfaces and all. Then the capillary rise method, this is used to measure the angle in small diameter grafts and these things, where all the surfaces having the uniform coating and uniform surface morphology is available. To check that, we use the capillary rise method. So, that we will use the meniscus to find the angle between the liquid surface and the solid surface. Then the Wilhelmy plate method, where we will have a plates, metal plates and all. If you check the contact angle, we introduce the plate. So, both of the sides will have the same angle and by that we can find out the contact angle. Okay. So, the advantages of using contact angle is very cheap and you can use it anywhere immediately after preparing a material surfaces and all. The major disadvantage is if there is a very rough surface or the surface is not uniform and all, it will have a different angle produced on different angle will be there. So, next technique is X-ray photoelectron spectroscopy, also known as electron spectroscopy for chemical analysis. It is a technique where you can find out what are the elements present on the material surface and all. So, if you have a material and you do not know what are the elements present on the surfaces and all, you can just do this analysis and it will show if you have a whatever metal ions or any other organic compounds present. So, it will show all the elements present in the material surfaces and all. So, this XPS is only for the surface technique where it will go up to a depth of 10 angstrom. So, up to that depth level only it can measure the elemental analysis. So, below that it will not have that elemental composition and all. So, this is mainly used when you are checking for contamination of a material surface, or if you are modifying a material surface and to check whether the introduced modification have a effect and all, you can check using this XPS method. It is a confirmation technique for all those applications and all. So, it works on the principle that when a X-ray is introduced onto the surface, it will excite the electrons, though the excited electrons will be detected using the detector, and it will check for it will show the binding energy based on the electron intensity. It will show the binding energy and analyze what category it belongs to, whether it belongs to carbon, whether it belongs to oxygen or nitrogen, sulfur and all. So, it works on the principle that binding energy equal to energy of the X-rays minus kinetic energy. So, this is an XPS instrument and this is how the spectrum will look like. So, in XPS analysis there are two categories, two types of analysis. One is wide spectrum analysis and another is a cold spectrum analysis. So, wide spectrum analysis you can identify the oxidation states and the elements present throughout the surfaces and all. So, like you can see at the top graph there is a wide spectrum analysis where you can actually see the oxygen, carbon, nitrogen, sulfur. So, if you have other elements present also, it will show that. So, it will be like a elemental percentage you can find out from this spectrum. Whereas, the core level spectrum where you can identify what type of chemical bonds formed in the carbon based spectrum. So, carbon based spectrum would be around 285 binding energy. So, if you look at the carbon based spectrum itself, so you can see that the peak each of the peaks is for the different binding. So, you have a for normal CC bond and CO bond and acid bonds and ester bonds. So, all these bonds you can find out using the core level spectrum analysis. So, by this core level spectrum analysis you can find out the oxidation state, valency of the valency electrons, valency state of the elements. Then if you are attaching a molecule, so you can find out whether the bonding has been properly done on the material surfaces and all. So, all those things can be confirmed using the core level spectrum. Okay. One of the disadvantage of using XPS is that the sample would be analyzed under high vacuum condition. So, if your sample is not stable in a high vacuum condition, it is difficult to do XPS. So, coming into microscopic techniques also involve comes under the surface characterization techniques only, but it has a wide applications like fluorescent microscope can actually see how the organelles and how the nucleus and all looks inside the cells and all. Then transmission electron microscope will look inside the material surface, not only the surface, looks inside the materials and all. So, to find out the morphology we primarily use the microscopic techniques, and each of the microscopic techniques has a different depth and different resolution it can go up to. So, it can go from atoms to the cells, which cells and normal materials you can go. The size will range from millimeter to nanometer, and some microscopic recent techniques and all have go up to Armstrong levels also. So, for light microscopy you can see up to 200 nanometer, and if it is a electron microscopy you can go up to nanometer size and all. So, this is a schematic representation of optical microscope and a fluorescent microscope. In optical microscope you will have a lens piece and light source, and you will keep a sample inside, and based on the light source the sample would be observed through the magnification piece and the objective piece to see the whatever sample you are observing. So, the optical microscope has a lot of types of phase contrast to check whether the cells would be in observed based on the phase difference between the cells, because the light would be the cells would be absorbing some of the light. So, that cells and all would be dark surface, and lights which are not absorbed by the cells would be a brighter side. So, that will have a phase contrast microscopy, and confocal microscopy based on the magnification parameter and those things it will vary. And fluorescent microscope, where you will have a fluorescence where you have a fluorescence exposed onto the sample, and if you have a fluorophore inside the sample, that will get excited, and that excited wavelength can be observed using the detector. So, the image shows the fluorescence microscope image. The image is a fluorescent microscope image, where you can, the green elements are the actin filaments, which are stained using palladium, and the blue stains are the nucleus, which is stained using Hoyt stain. So, if you are having a experiment where you are involving nanoparticle encapsulation, or if you are introducing a drug into cells and all. So, whether the drug has been properly introduced into the cells or into the materials and all, if you want to find out, you attach that drug with the fluorophore, and if you observe under the fluorescent microscope, you can check whether that actually happened or not. Okay. So, both of those techniques has a lower resolution only. You can go up to 200 nanometer only, you cannot go below that. So, for that purpose we go into scanning electron microscopy. So, this is a schematic representation of the scanning electron microscopy. The major difference is that here you have a electron beam as the light source. So, you have a electron beam which is passed down to the electromagnets, which will control the electron beam, and it will focus on your sample, and based on the sample property you can observe the images. Okay. So, there are two types of detection available in scanning electron microscopy. One is secondary electrons and another is backscattered electrons. So, secondary electrons is that whenever your electron source is given, and that it will go into the it will excite another electron, that scattered electron will be observed under secondary electron detector. So, that will have a secondary electron source. Then for backscattered electrons, the electron which you are giving, so some of them would be reflected by the sample. So, the same electron when you are detecting, that is a backscattered electron detector. So, why these two are? So, when you are having a when you want to see the morphology very in detail and all, so you want the electrons which are repelled by the surfaces and all. So, that will have only the morphology of the surfaces. So, secondary electron will have a depth and all. So, when you have a porous structure and all, if you use a secondary electron, it will have a better image. When you want to just observe the morphology and all, you can go for backscattered electrons. Then Auger electron spectroscopy, which is another totally different type of spectroscopy, where the detection is based on Auger electrons. So, Auger electrons are the electrons which are excited from the core level will be replaced from the outer electrons. That electrons will produce the energy. So, that will be observed under the detector. So, that will show the atomic composition. So, if you are having a copper or any other metals available, so those metals it will show how much of the things will be available, density. So, based on that Auger electrons, because based on the copper, one copper if it is releasing some amount of electrons, if the composition is high, it will release a certain number of electrons. So, that will be observed under the Auger electron microscopy. In scanning electron microscopy also you can find out the elemental composition, where it will show the percentage of elements present on the surface also. Okay. So, that is called X-ray energy dispersive method. So, this is how the SEM images looks like. So, you can see the first 5 images are where the blood platelets are adhering on the material surface. So, this is A is a control sample and all these 4 are the different treated samples. So, modification different techniques has been used. So, after the techniques the platelet adhesion has been reduced. So, that can be observed under scanning electron microscopy. Then the bottom one is a vascular stent where they have coated a material onto the stent. So, to observe the coating has been properly done on the vascular stent, they have observed using scanning electron microscopy. So, there are 2 parameters which are important in microscopy, one is magnification and another is resolution. So, magnification determines how much of a magnify you can do a sample and all. Resolution determines how detailed your images are. So, magnification depends on the instrument property and resolution it depends on magnification, but how detailed you can go observe, because in scanning electron microscopy if I go above 10 nanometer size and all, the image will not be detailed. So, you have to go for the higher end equipment. So, to have that it will have that magnification, but you will not have a clear picture and all. So, resolution is very important when you are looking into microscopy. So, TEM it also works on the similar principle as SEM, but the idea is that the electron beam will be passed through the sample. So, transmitted through the sample, that is why it is called transmission electron microscopy. As you can see in the SEM, the sample is at the bottom and if it is reflected based on backscattered or secondary electrons, the images would be observed. But in transmission electron microscopy, the sample would be at the center and the electron beam would be passed through the sample, and that will give the what is present inside the material and all. If your material is porous structure and all, that the electron won't have any inhibition passing through that porous structure and all. If you have a materials compact materials and all, it will based on the density of the material the electron will have a passing transmission will be varying. So, based on that the image would be observed under the transmission electron microscopy. Then coming into scanning probe microscopy. So, until now we have observed based on the light source, then electron source. Then scanning probe microscopy is where you have a probe which will have a feedback on the from the surface and it will input into the detector and it will form the images and all. So, scanning microscope has a lot of different techniques based on the application. So, one of the widely used scanning probe microscopy is AFM, atomic force microscopy. In atomic force microscopy itself, it is having a different types such as non-contact, contact, tapping methods. Those 3 techniques are available in atomic force microscopy. Then, so these are the techniques available and the uses based on the techniques what are you want to observe. So, we will see atomic force microscopy. So, atomic force microscopy, the cantilever is there. Cantilever is a small sharp object, piezoelectric object which will expand and contract based on the voltage applied onto the cantilever. So, when your material in contact mode, if you are having a material and the cantilever would be placed on the top of the material. So, if it is in a flat surface, so the material will move along the flat surface and it will have a straight without any movement, the voltage difference would be constant. So, it will have a flat image and all. So, if you have a rough surface and all, it will move up and down. So, that will have the voltage difference that would be detected using the detector and it will have that rough image surfaces and all. In non-contact mode, what actually happens is that the cantilever will move at a frequency within the resonant frequency of that cantilever, and based on the surface surface of the material, the movement would be inhibited by the electrons on the surface of the material. So, that difference would be observed under the voltage difference that will have a imaging atomic force image. That is a tapping method which will be within the resonance frequency. In non-contact mode, it is also vibrating at a high frequency above the resonance frequency, where it will not touch the surface at all, but the van der Waals force and other long range forces available on the surfaces will have a effect on the non-contact mode. That effect will be observed and changed into a image. So, those are the three different things. So, why these three different things are available is some samples would be very sensitive. So, if you are observing under the contact mode, the sample will get damaged. So, to avoid that, people will go for tapping mode usually. Tapping mode is one which is widely used. Non-contact mode, when you have a sample which is very sensitive, you do not want to touch the sample at all. So, these are the three different techniques. So, this is a schematic representation of AFM, and this is how the image looks like. So, you have a plane surface which is A, and it has some ridges and all seen, and if you modify the surfaces, it will have a rougher surface that will be observed as a 3D contour. You can see that images and all. So, coming into Fourier transform infrared spectroscopy. So, when a molecule is exposed to IR radiation, it will exert vibrational stretching, contraction and bending and all. So, those molecular properties can be converted into Fourier transform infrared spectroscopy spectrum. So, if you are having a molecule methane CH3, if you are exposing it into IR spectrum, that molecule will have a different bending based on the bond between the atoms. So, that can be observed under the FTIR spectroscope. So, there are different types of stretching. One is symmetric stretching, asymmetric stretching, scissoring and blocking. So, if you are having a highly nucleophile, it will have a repulsion between the neighboring nucleophile. So, that it will have a stretching observed onto the observed, that will be observed under the FTIR spectroscopy. So, the different methods of FTIR. So, FTIR can be used for surface technique also and for bulk composition also. So, if you are having a material surface, want to check the functional groups. So, each functional groups will have a different stretching and bending. So, based on that we can identify the functional groups. So, it can observe for surfaces also, it can observe for powder samples also, it can observe for scaffolds and liquid samples also you can do under the FTIR analysis, where you. So, I will first explain the methods. So, transmission FTIR spectroscopy is the widely used method, where you keep the sample in the path of the IR and it will detect the spectrum, and it will show how much of the light has been transmitted through the sample, and based on that it will plot the spectrum. Then ATR FTIR spectroscopy is the attenuated total reflectance, where you have a reflective surface at the bottom, where the light source would be reflected to and fro through the sample and the reflective surface, and the final amplified that reflection will be detected using detector. Then drift spectroscopy, it is diffuse reflection infrared Fourier transform, where the it is similar to the transmission FTIR spectroscopy, but it would be up to a particular depth, it would be diffused, the IR rays would diffuse and then it would be reflected back into the detector. Then reflectance micro FTIR, which is a new techniques, where which is a new technique where you have a very micro sample which would be which has a high sensitivity, where the IR source can be reflected and it can be detected for a very small amount of sample with high sensitivity. So, for liquid sample you can form a thin film, like there would be a casing where you can drop the liquid onto that casing. So, it will form a thin liquid film and that can be measured using transmittance FTIR spectroscopy. So, if you are having a film or material opaque material and all, you can, because transmittance it has to IR has to pass through, there should be some IR has to be passed through. If it is completely blocked, you cannot observe any spectrum. So, to have to avoid that obstacle, we will use a ATR FTIR spectroscopy, which will have a reflective surface so that if your material is highly opaque, that will show the spectrum, produce the spectrum. And for the transmittance spectroscopy, we use KBR as a molecule, because KBR has a IR background which is standard for all the IR. So, if you are mixing the KBR with your sample and checking for the spectrum, that will have a background, KBR would be reduced. Okay. So, this is how a normal FTIR spectrum looks. This is an example of toluene, where you have each of the CH stretching, CC stretching in the aromatic ring, because CC at a normal bonds it would be differ, and it would inside aromatic ring the stretching would be constrained. So, each will have a different wavelength. So, different wave number. So, based on that we will identify what are the functional groups present. So, these are the commonly available functional groups. So, each has a different frequency available. So, alcohols and carboxylic acids will have a range at 3000 to 3300 centimeter inverse, and if you are looking into ester bonds and amine bonds and all, you can look into around 1700 centimeter inverse and all. So, FTIR technique will show what are the functional groups available, but if you are preparing a new material which is having same functional groups and all, then it would be difficult to know, because the same functional groups will overlap with each other. So, you cannot have the exact mechanism to be found and all. So, it is an technique where you can optimize the reactions and all, but you cannot fully depend on FTIR. Okay.